Okay, so I'm recording. Welcome everybody to session number 1 for understanding analysis. We will obviously be talking about chapter 1. So a couple things just to start with, right? So the general way we're going to do this is I'll go over, first of all, I'll probably talk over the actual book, like scroll through the book. Do I have it here? No, that's my own stuff. Let me open it quickly here. So of course if you haven't already, oh, there it is. The texts are available. So we're today talking about chapter 1, and generally, maybe I'll talk over the book. I'm not gonna read the book. I'm just gonna talk over it, just to have something to point at and look at. And then we can, as we're going through, maybe we can stop and talk about proofs here and there, like certain proofs that we find interesting, and then maybe some exercises. I think maybe we keep the exercises maybe to the end, just so we go through all the content, and then we'll come back. We'll loop back around and then do some exercises that I might find interesting. That's just my idea. If anybody has a better suggestion or anything like that, or just a different suggestion, then please feel free to let me know. Everybody's very welcome to unmute and talk, or message me, or message in the just chat for the Discord call. Hope to maybe work on some of these exercises together, because again, I'm not a master of this stuff. This stuff is not totally trivial to me, so it's good to work as a group. But nonetheless, I'm happy to run the sessions. This is the kind, like this book and the Linear Algebra Done Right, both these books are books that I've been half reading for a year or something like this. And I thought, I think working as a group with people is a good way to get over that. So, yeah. Okay. So, I like to talk, so I will keep talking if nobody stops me. But if somebody wants to stop me, then please feel free. In general, I think maybe for I think it's good to kind of like maybe work as a group on some of these things, right? So maybe for some of the proofs, maybe I can, I don't want to be too teachery, but maybe I can just like say like, what do people think, and try to contribute to the proofs, and then especially with the exercises. Anyways. Today will just be a little bit of a shorter session, so we're just going to kind of go through things. We're not going to go into too much detail about everything, but yeah, that's pretty much that. Okay, I am recording. Everybody can see my screen. Everybody who wants to be here is here. I think that means we're good to go. So unless somebody wants to shout and stop me, I will start talking about the real numbers. So chapter 1 of this book, right? Analysis. Analysis means we are studying, these kind of continuous looking things. So the real numbers are the quintessential continuous looking thing, and of course one of the reasons this even comes up at all is because, it comes up for a lot of reasons, but historically the reason why it comes up is that there is no square root of 2, right? That's not a real number. That's not a rational number. Sorry, it is a real number. That's not a rational number. So blah blah blah. We're not going to go through the proof of that, because that's you could say it is known, and that would be enough of a proof of that, right? But that then begs the question of okay, so where is it, right? If it's not in Q, then it's outside of Q, but where is it? So that's how we, that's a motivation of where R comes from, is that we have to kind of fill in those gaps. And so this is maybe an important part, right? For the moment, it is not too inaccurate to say that R is obtained by filling the gaps of Q. Q is all the rational numbers, all the decimals that we can think of. And there's a bunch of gaps in it, right? All the roots and all the cube roots and all the fifth roots and blah, 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 except for the obvious ones, right? Except for the ones that are natural numbers. There's a bunch of gaps. And there's a lot more than just the roots, right? We'll talk about it, but in a very real sense, Q is mostly gaps. So R is what you obtain by just saying, well, what should be in those gaps, right? And we define the number as the gap itself in a way. Anyways, we're not going to talk too much. I had a brief discussion with another member here, right? Just before we started about this first chapter, we actually don't define R. Right? We have a functional definition of R, but we don't have a formal definition of R. And the definition goes mostly that R is, there's a lot of things you can say, right? But R is the one and only complete ordered field, right? And the completeness we will define, and ordered is, we will define, but it just means it has an order relation. and it is a field, right? So its operations obey certain rules. The rules that, maybe you can call the obvious rules, right? The rules that we expect. Again, I know, I talk a lot, but, feel free to butt in if anybody has anything to say. Or if I'm saying something wrong, I don't know. Maybe I'm saying something wrong. Anyways, so it's discussed in section 1.3, which is what R is, but it's formally defined in 8.6. So that'll be weeks from now. We can talk about it weeks from now, and that might be even a whole session just we talk about 8.6. Because it can be really complicated actually getting to the crux of it. But for the moment, it's fine to say that R is filling in the gaps of Q, and we'll have an even better definition than that in a second. So no proofs in 1.1. Then in 1.2, it's a bunch of preliminaries. So this is some set stuff, which again, maybe not really the point of our exact group here is not really to talk about the preliminaries. I mean, we're assuming people have some preliminary knowledge. This set's pretty important though, right? So let's take a look here, right? S, which is all a set of rational numbers whose square is less than 2. So you can imagine here, right? Like we have Q, right? So how do you think of Q first of all? Right, Q. Well, Q is, I mean, it's not a number line. R is the number line, but it's kind of like a number line with a bunch of holes in it, right? You can think of it like that. That might not be the best drawing of it, right? But it's a number line with a bunch of holes in it. And so we can see that maybe here is the number 2. And we want all the numbers whose square is less than 2. Whose square is less than 2. Square is less than 2, right? So, that'd be something here, right? If I square this, then maybe I get something there, but it has to be less than 2. So it's not this section, but it's some portion here, right? The square root of 2 we know is 1.4 or something. So it's, well, that's probably actually a bad drawing then. It's not really where 1 is. That would be 1, and that's like 1.4, right? That's like 1.4 approximately. So everything here, when you square it, it will be less than 2, right? Up until this certain number, but not including that number, right? So that number, that barrier itself, right? That barrier is the square root of 2, which is around whatever, let's just say 1.4. And notably that is not an element of Q. Okay, I don't want to drag on if something's obvious or something like that, so I'll just kind of keep talking. But anyways, this is an important set, and so we define the supremum of this set to be the real number root 2.
Yeah, by the way, I think you have to include as well the negative side of Q. That also
yeah, right. So it would be, well, where would it go until? It would go until here, like negative 1.4.
Yeah.
Around, obviously we're approximating, but around negative 1.4. So that section there would be our S, I guess, right? Because when you square negative 1, you get 1, which is still here, right? Yeah. So yeah. So that's like our S, right? S. This is S, right? Okay. So, nothing really. I don't want to talk about set theory too much because set theory is maybe not the purpose of the course here, right? So, infinite unions, infinite intersections, blah, 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 blah. We will talk a lot about infinite unions and infinite intersections. We, of course, have De Morgan's laws for sets and blah, blah, blah. If I say blah, blah, blah and somebody wants me to talk about it, then please tell me. Otherwise, I will just keep going. So for functions, of course, functions are important. So I like this, I like... I teach a lot of high school and they talk about functions and things like this, right? And so I like giving them what do you think of function? What's the definition of function? I toss them. I don't try to break this definition apart. I just try to maybe show them something like this and not to just sound smart, but to maybe show them that there's formalizations of what it may be familiar. So anyways, I'm sure everybody's familiar with that. This is a great function. This is like the function in analysis. I mean, there's a couple that are the function in analysis, but this is a great one, right? Does somebody want to, I don't know, toss it out there, and I might get crickets, but does somebody want to take a shot at just describing this function? How would you draw this function? What is it doing? Maybe not, uses for it maybe, but anyways, what do you think?
I would like to try.
Sure, let's hear it. That's great.
I imagine this as you can think of it as like two horizontal lines of dots, I guess.
Right.
Um,
I'm with you.
one at y equals 1 and one at y equals 0. Well,
Yeah.
kind
And
of.
why is it dots?
Because they are discontinuous.
Yeah, right. So it's kind of like I'm with you for sure. So if you don't mind, I'll keep describing what you're saying, right? So it's like there's no, so I drew little set, like it looks like little lines, right? But I'm really like, I just mean dots. I mean like dust in a way is the word we often use, right? So it's just like, it's just a bunch of little specks because yeah, like so g of 1, right, is clearly equal to 1, right? Because x1 is a rational number. But you know, g of so the next number. Now, whatever you want to call the next number, right? 1 plus epsilon, right? Well, if epsilon's a real number, right, then we don't exactly know. But you know, like we could say g of root 2 would be 0. But g of 1.414 dot 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 dot, well, no dot dot dot, but you know, close to it, something close to root 2 is going to be 1. And if you take any rational number that's getting closer and closer and closer to root 2, they'll all have a value 1. But actually at root 2, it'll be 0. And so we call this like a it's like yeah, it's discontinuous. I think it might be continuous at 0. I forget what I forget that now. We'll talk about that probably in chapter 4. I think it's continuous just at x equals 0. Someone correct me if I'm
By the
wrong
way,
there. Yeah.
Like, you know, I have some troubles with this drawing, because okay,
Tell me,
it's
yeah.
true, yeah, that there should be some kind of like lines with punch holes, but in the case of the rationals, they are countable. So you know, so yeah, like having the points that you can enumerate actually is okay. But then I don't know how to actually draw it for y equal 1, because the real numbers are not countable, right? And the real numbers minus the rational numbers are not countable either, obviously. So I don't know how to actually draw it.
Yeah.
Because drawing the points actually
You're
gives
right.
the false notion of countability.
Yeah. You're right. Because looking at this, you're like, well, you know, all these, there's a dot up here for every rational, for every rational. There's a dot up here for every rational number, and there's a dot down here for every real number. But that's not really quite right, because yeah, there's a dot up here for every rational number. Yes, right, because the rationals are countable, but the reals are uncountable, and whatever's left of the reals, the irrational numbers, right, whatever's left of the reals when you take out the rationals, is still uncountable. So it's like there's mostly gaps, right? It's heavy on here, right? This is actually where most of the dust is, right? So it's like you know, I don't know how, exactly the words, but we can just say here it's actually like a stronger distribution, and here it's a weaker, right? Because this up here, this represents Q, maybe a bad color, so let me choose a just different color here. Q is countable. And then here, I, you know, which is R, well, I don't know how you want to describe it, right? But let's just say R minus Q is uncountable. It's a pretty simple proof to do, right? A pretty simple statement. I mean, we haven't actually shown that R is uncountable yet, of course. We haven't really even talked about R yet. But so it's heavy here. There's a lot more dust on the bottom here. But there's no continuous segments except at x equals 0. I might be wrong. Maybe we can find this. I just, in my head, I have it that at x equals 0 is continuous. It might be a different function, but anyways.
Yeah, I think it's a different function, because like in this function, you can just always shift x by something, and then if you shift it by a rational number, if you shift x at 0 by a rational number, then you get another rational number. And if you shift it by an irrational number, then you get an irrational number. So in a way, the state of continuity in every point should be the same as in 0.
Right. Okay. I see what you mean
some
there.
Kind of symmetry to shifting.
Okay. Yeah. I see. You're right, because it is the same there. Right. So maybe not. I now I'm a little bit thinking it might be this function when you put x there. That will be the one that's continuous at 0. I think that might be it. Yeah, that makes sense, actually. I think that's the one. So not the function, but x if it's rational, or maybe x is, no. Anyways, we'll talk about that function probably in chapter 4 when we talk about continuity and stuff like this, but yeah. Okay, I'm going to keep moving. a thank you to there's people who are contributing all that. It's nice to hear people, but obviously no pressure, but nice to talk to everybody. So triangle inequality, absolute value, blah blah blah. Very very basic, just kind of algebra of this stuff. But the triangle inequality is extremely important. I mean, it shows up so many places, right? So this is a basic fact about metric spaces, that we have a triangle inequality that works like this. And so the real numbers is maybe the first time you get a feel for the triangle inequality. So I think it makes more sense to talk about that in an actual what's it called? An actual example. This is the first theorem, quite basic. I think I don't know. Hopefully people can maybe go through that on their own. I don't know. That's maybe not worth our time to talk about. And then of course there's induction, and we will talk lots about induction, especially in chapter 2 when we talk about sequences and things like this. So it's not too crucial. Okay, so that's that. And again, we'll maybe pass through these exercises a little bit later. Okay, so now axiom of completeness. So what exactly is a real number? That's our maybe our goal here. So we'd like to have an initial definition of R. That's literally what it says here. There you go. That will be our functional definition. So if I talk about a real number, I have to know what that does. What that is. So in my head, like just my definition that I work with is like R is the only up to isomorphism, if I can spell isomorphism, complete ordered field with Q as a subset. Right. So that's what I would say, and there's lots of other ways to formalize it, right? And you can construct this set using Cauchy sequences of rationals and blah blah blah. But this is kind of my I think this is a fine working definition. So we have to kind of break this up. So the only up to isomorphism doesn't really matter, right? So up to isomorphism just means that there could be other sets that act the same structurally, but they're just relabeled versions of this. I don't actually know how to prove that, but that's maybe not something I have not done before. That it's the only one. But anyways, it is complete. So we have to describe complete is actually a really very loaded word here, right? Because I mean, I could just define this as whatever I want, and that's the property I'm giving this set. But there are specific things we mean when we say complete. Ordered, it means it has an order relation. And field means it has the property. It has an addition and multiplication that work the way we expect it to. We can talk about that. And it has Q as a subset. So let's see if there is there any. Let's see if there's any. There's no actual list of all the field axioms, right? But maybe I'll just look that up. Field axioms. So the field axioms, whatever, this one's probably best. It's all this stuff, right? So we have, it just means that our set has an addition and multiplication operation that obeys this kind of, these details here, right? And actually defining the addition and multiplication operations requires actually the construction of R, right? What's the actual construction that we're working with? So if we're using Dedekind cuts or if we're using Cauchy sequences, then we have to define what that means. And so we're not going to talk about that right now, but just we are saying that there is some addition and multiplication that obeys these rules. And these are the rules. All the usual things, right? So, okay, again, maybe take this. Can I just copy image and then just paste image? Okay, so that's what field means. And complete is the whole thing, the point of this section here is that we're talking about what complete means. So this is our initial definition of completeness, which we'll highlight, and this is going to be our functional definition of completeness. I mean, it's the axiom of completeness, right? It's just like what we mean when we say completeness. At the start at least, which is that every non-empty set of real numbers that is bounded above has a least upper bound. Right, so we call that number the supremum. is there, where are we? Here's supremum. Yeah. So maybe we can look at an example. Probably is the best thing to do here. How should I? What should the example? I mean, this is the quintessential example, right? So maybe we can talk about this a little bit. So, if I think, well, it's not actually, it's not always that, but if I think about, you know what? Actually, let's talk about instead. Let's talk about S again, right? So S is this set. R is in Q, such that R squared is less than 2, right? So first of all, this set S is bounded above. S is bounded above, right? So maybe we can just prove this quickly, right? So I say indeed, if R is in S, this means that R squared is less than 2, right? Which is less than, let's say 4, right? So that means R squared is less than 4. So that means that R is less than 2. Let's just say that. You can put whatever square you want here, right? So we know that every element of this set is definitely less than 2. What that means is that I can draw this. So if I imagine, again, maybe it's my kind of number line, but only the rationals. That's 0 right there. And if this is 2, then I don't really know where S is, right? I don't know if S is like this or if S is like this. I mean, we've already discussed it, right? But I certainly know it's all over there, right? It's bounded above. There's nothing past this way. S can only be in this kind of segment here. S is in here. And what that means really is that we can attempt to squeeze this upper bound, right? We can attempt to squeeze this upper bound lower and lower and lower and lower, right? Because you could attempt to do something like if R squared is less than 2, which is less than, well, some I don't know. I don't know if I'm going to be able to think about it fast enough, but it's like, 9 over 4. Is that true? 9 over 4 is, yeah, that's true. Right. So that means that R is less than 3 over 2, which is 1.5. So we can actually, we can squeeze this. We could squeeze this down to 1.5, right? But how far can we squeeze it? That's the question. Can we keep squeezing this upper bound, right? This upper bound here for the set lower and lower? The answer is that for the rationals, we can't. There's going to be a point where for the rationals, we can keep doing it, right? There's no smallest amount we can squeeze it. But for the reals, we call that endpoint, that limit that we're getting to, the thing that we're kind of like squeezing this upper bound. We call that the supremum of the set, the least upper bound, right? So the supremum of a set S is the least upper bound. Right? So you see S, we could say that this S that we're talking about here, right? So upper bounds for S, I showed 2 as an upper bound, I showed 1.5 as an upper bound. But can we keep going? This list, right? Can we keep getting smaller and smaller upper bounds? The limit, the smallest one, is the supremum of the set. So that's really the really key thing about what the supremum is. So I don't know if that makes sense. Again, somebody yell or stop me if that doesn't make sense. Excuse me. But that's the idea of a supremum. Or if I said something wrong, again, please tell me. So the important thing here is that the set might not contain its supremum, right? So 0, 2, right? The supremum of the interval 0, 2 is equal to 2. Why? Because 2, we could prove this, right? Because 2 is an upper bound, for S, and because 2 minus epsilon is not an upper bound for S, for all epsilon greater than 0. Because what I mean by that is like you take any number smaller than 2 and it's not an upper bound for the set anymore. Take 1.99. Well, 1.99999 is in the set and is a bit above, so that wasn't an upper bound that we started with. But importantly, 2 is not an element of the open interval 0, 2. Whereas here, the supremum of the closed interval 0, 2 is still 2, but 2 is also an element of the closed interval 0, 2. If the supremum is an element of it, then that's the maximum of the set. That must be the maximum of the set. So the word maximum, supremum are different here, right? So every set of real numbers that is bounded above has a supremum. If it's not bounded above, then it might not have a supremum. It could be unbounded, right? The open interval from 0 to infinity. Well, that's that's unbounded. It doesn't have a supremum. But if it's bounded above, then it'll have a supremum. It might not have a maximum though. That's maybe where I was planning on going there with that sentence. It doesn't have to have a maximum. So here it has a maximum, but here it doesn't have a maximum. There's no maximum value because maximum means it's in the set. Supremum doesn't have to be in the set. Okay. Well, if nobody has any questions or anything like that, then I'll just keep moving. So, well, here we go, right? This is what I was kind of just keep talking about. So maybe I didn't really have to talk about that. Yeah, this is definitely how I would formalize working with the supremum if I was asked to prove that something is a supremum or something like that. Obviously, it depends on the situation, but so if you have an upper bound and you want to prove that it's actually the supremum, then you show that any element that's smaller is not an upper bound. That's basically the definition. It's basically rephrasing the actual definition.
Is it only me, or did everybody lose the audio?
Oh, I don't know. I heard that.
Yeah, the audio was fine for me.
Audio is fine for you, so
I can still hear as well.
okay, good. So I think maybe it might just be you, the one person. Okay. So we'll come back to the exercises at the end, of course. How many sections are there in this? 1.4 to, yeah, but 1.6 is not crazy. So, okay, so, 1.7. So we really only have 3 more sections here. And I think here we might get into actual nice proofs. Yeah, I like the density, of course. Density proof is good. That's good. And the existence of squares. I definitely want to do this proof. I like this proof. It's one of my favorite proofs, I think. So there you go. Okay, so yeah, let me see if I can find it quickly. Let me just find a document here quickly. I don't have it here. No, I'm sure I do. Where is it? Give me 20 seconds to find what I want to show here. I can't find it. Of course I can't find it. Well, I made this little document is what I'm trying to show. I made this little document. and it shows all the different formulations of completeness. But I'm not going to be able to find it here, of course. So that'll, I'll maybe show it for next time. I don't know. But okay, so sorry, I didn't mean to sidetrack us so much like that. We have our one definition of completeness, which is that it is every bounded above set of real numbers has a least upper bound. Nested interval property is equivalent. So we use the axiom of completeness to prove the nested interval property, and we can do the reverse statement as well. Or at least we can do the reverse statement as well. So nested interval property is good, and of course we can talk about that proof. But then we move on to the density, right? Density of Q and R, right? So we would say that Q is dense in R, and what that means is that between any two real numbers, there's always going to be at least one rational number, right? So between any two distinct real numbers, right, there will be a rational number between it. And that might be a fun proof for us to go through. And then the last part, I think, of this section, is that basically there exists a real number, alpha, that is the square root of 2. The square root of 2 is a real number. And remember, what we mean with the square root of 2 is this, right? That alpha satisfies this equation. Sorry. So I don't know. I think maybe now is a good time we can just take a second and I got a sound effect. Thank you.
Sorry, I was trying to react to the thumbs up, but it just started going.
That was good. That was good. No. I like the excitement. It's a very exciting sound effect. So if everybody's, unless I hear any complaints or yawns or something, I'll maybe do, I don't know, we could do the proof of, I don't know what proof you want to do. We could do the density proof.
I think the density Q and R, it's been hyped up.
Yeah.
Would be cool to see.
Okay, let's do it. Sounds good. And so, I mean, I'll refer the text a little bit, right? But I like to kind of maybe do it my own way. The thing about proofwriting, and depends on how much proofwriting you've done, but you get 10 people to write the same proof, then it'll all be different, right? Sorry, to get 10 people to prove the same fact, same theorem, the proofs will all look different. It's extremely, based on personal taste, and there's an art to it, right? So that's why hopefully it's still interesting to hear me go through the proof. Of course, my proof strategy is going to be pretty much the same as in the text. I'm not going to apply some more complicated techniques or anything like that, but maybe I'll explain it a little bit more. Okay, so what are we trying to prove? For every two real numbers a and b with a less than b, there exists a rational number r satisfying this. Right. So before we get into the proof, right? So it's just like if I take any two real numbers, right? So if I take root 2 and root 3, right? And I want to find a rational number between them, right? Which one's bigger here? This one's 1.4 something. This one's going to be bigger, right? So this is going to be some bigger number. So this could be like our A. This is like our B. I need to find some method. I need to have some technique that always works to identify some m over n that is strictly between root 2 and root 3. I need some strategy. Yeah, that's what the proof is some strategy that always works for me to be able to tell you this fraction is between those two numbers. Okay, so let's just kind of logic it out here a little bit. Let's just see how we're gonna do this. Let's just think on the number line, right? So I can think of the proper number line here now, right? So this is proper R, like this. And if I have, and I'm going to use root 2 and root 3 for just as the example for now, right? If I have root 2 and root 3, right? I want to be able to land some fraction. It doesn't have to be right in the middle, right? It doesn't have to be right in the middle, but some fraction that's right in the middle, m over n. Well, the first thing that I'm going to need to do, right, is I need the denominator to be the right size. I need it to be big enough so that I don't overstep this, right? So if n, right, let's say n was, it was 1 over 2 or something like this, right? Then 1 over 2 is gonna look like this, right? So it's gonna be like this is 1.4 or something, right? So it's gonna kind of look like I don't know what root 3 is. I might have it too far. But it's going to kind of look like this. And then I'll have a few steps in here. So 1 over 2 would work, right? That would be fine. But you can imagine if these two numbers were really, really, really close together. The point is that it has to work for any two numbers here. If these two were really, really close together, let's say that was there and that was there, then a half would be too big, right? So if this was a half, then a half would overstep the entire interval, right? So my denominator would have to be something bigger than a half. Okay, so maybe just for the sake of exposition, I can use the diagram that's here, right? So this is the diagram from the text, right? So I need my denominator to be the right size, right? So if I make this denominator bigger, then these intervals get smaller, right? I need it to be small enough so that there's at least one little peg here, one value for the numerator that lands in between them. If it's too big, it might just overstep it, right? So that's kind of maybe the first part, which is choose a denominator small enough to fit in between A and B, right? And so to do that, we want to pick n in, right, this is, a natural number n, such that 1 over n is smaller than the distance between them, right? And we want the positive distance, right? So we want the space between them. We want one little segment to be smaller than this distance, because if worst case scenario, this peg lands right before A, as long as the gap size is smaller than this distance, the next one will land in between somewhere. So we want this 1 over n to be less than b minus a. But, can we do this? Can we do this? And maybe I'll leave that as an open question for a second if anybody wants to chime in. Can we do this? How do we know we can do this? I want to pick an n that has this property. But can I just say whatever I want and say that there's an n that has this property?
Yeah, we can do it. It's just the Archimedean property. Given b is greater than a, then b minus a is greater than 0, which which means that you can always choose a natural number such that its inverse is less than b minus a.
Exactly. So that's exactly what the Archimedean property says, and we didn't mention it yet. So that's what the Archimedean property tells us. So this point 2, given any real number y. So for us, y is b minus a. B minus a is a real number. How do we know b minus a is a real number? Well, that's the field properties, right? The field axioms. So b minus a is a real number. That's our y. Then there exists an n and n such that 1 over n is less than y. Great. So convenient, right? It basically just means that the rationals can get as small as we want. We can get a really small rational number, right? So there's no, it's not like the reals can get so close together that the distance between these two real numbers is smaller than any rational number. That's not true. The Archimedean property tells us that that's not true. So we have that here. The Archimedean property is very, very simple to prove. Because it's a little bit obvious, right? So yes, we can do this because of point number 2, and that's like our y. That's basically pretending to be our y. Great. So I'm going to when I do this, I like to say, okay, fix n equals n naught such that 1 over n naught is less than b minus a. And we know that there is some natural number n naught that works like this. So coming back up to this root 2, root 3 example, right? If I take root 3 minus root 2 and I punch that into a calculator, I don't know what it's going to be. Let's just do it here, right? So if I take, is it going to let me do it? No, it's not going to let me do it. It's going to be annoying. Can I do that? Root 3, should I put some brackets maybe? Minus root 2. Yeah, there you go. Oh, no, equals. There you go. 0.3 something, right? This is, let's just take the first few decimals here. It is approximately this. So yeah, I can pick, so 1 over what? 1 over 2, no. 1 over 4, 1 over 4. Great, right? 1 over 4 is less than 0.317, blah, 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 right? So there is a way that 4 is my n naught. N naught equals 4 in this case, right? There is a way to pick it such that this fraction is going to be less than the difference between these two. In general, there always is a way, and it's because of the Archimedean property. Great. So we know this is true about n naught, right? We know this is true about n naught. There is a way to do this. So we and remember what we're trying to do, right? Did I write it up here? Yeah, we're trying to prove that there's always a way to find an m over n for any a and b, right? So let's just say here, maybe move back up to here, right? So if I have a less than m over n less than b, then there's a way for me to pick m and n. Well, I've already picked n, right? I've already picked n. I now just need to know how to pick m. Well, I guess I also have to show that this satisfies this, but that's not too crazy. We'll do that in a second. So let me actually open up my own notes here, because I think in my own notes I have it written. So give me a second to look at the notes here. So, okay. Now, remember, the thing we're trying to prove is that, so a less than m over n less than b. This is the same thing as a n less than m less than b n, right? But we fixed n, right? So we can put an n naught here, right? We've already fixed n. So we need to pick an m, pick m equals m naught, such that m, m is greater than a n naught. Again, we are able to do this for almost the same thing, for pretty much the same thing. If you want to invert both of these, you can invert both of these, right? All right, and then we can fix m naught such that this is true. This is Archimedean property, right? But you can also just do it this way. It doesn't really matter. Either way, we are allowed to do this, right? Like this is allowed once again, right? Again, yes, for the Archimedean property. So now we have that, okay, we have that m naught satisfies this inequality, right? We have n naught such that 1 over n naught is less than b minus a. And we have m naught such that m naught is greater than a n naught. But we're not just going to pick any m naught that does this. Yeah, there's the thing that I was forgetting. Okay, we're not just going to pick any m naught that does this. So if you imagine our, here's a n naught, and we want to pick, here's our number line, right? We want only natural numbers here, right? But anyways, let's just talk about this. There's lots of natural numbers after this. There's no biggest natural number, right? There's a n naught. This could be some real number, right? Because a is a real number. I mean, it is pretty much. And I want to pick above this here, right? I have a set. All of these are the natural numbers. These are maybe our candidates. Candidates for m. And I want to pick the least one, right? So pick the least one. Because I also don't want m to be too big, right? That's the important thing. I don't want m to be too big. And because it has to be smaller than this b n naught. And it won't be bigger as long as I pick the smallest one here. And we can prove that, right? We can prove that it won't be too big. Now, again, I'll pass the question to you. How do I know I'm allowed to do this? How do I know I can pick the smallest, how do I know, the smallest such m exists? Because I could say take the biggest one, right? I could tell you right now, give me the biggest M that satisfies this. And you wouldn't be able to, there's no biggest one, right? Give me
Yeah,
the
but
biggest M.
then,
But I
right.
need the smallest
So
one. Yeah.
in a way, the completeness is trivial for the natural numbers, and in this case, the bound it's a lower bound, so you can pick the
Yeah.
inferior of the set.
Well, you're right. So I think it's obvious, right? But that's what the well ordering principle is talking about, right? So if I, well ordering principle, is it well ordering principle?
Do you mean that every partially ordered set is contains a least upper bound?
This one, well ordering principle states that every non-empty subset of non-negative integers, natural numbers, contains a least element. So if I take the natural numbers and I take any subset of them, there will always be a smallest element in that set. Which I think is obvious, right? So if I take the numbers 0 to infinity and I just pick some of them, there will always be one in what I pick that is the smallest. There will not always be one that I pick that is the largest, right? So what if I just pick all the even numbers? Well, there's no largest one. But there is always one that'll be the smallest. So if I pick all the even integers, even numbers, then it'll be 2, right? So this is the well ordering principle of n, right? Now that is maybe that could be a defining feature of n, right? You could take that as a definition. There's a way to construct it, right, with that property, but that gets a little set theoretic, and we're not here to talk much about set theory. But we are allowed to do this because of the well ordering principle of n. Okay, so not only do we know that m satisfies this, m naught satisfies this, but it is the least element that satisfies it. So m naught minus 1 is smaller than a n naught. We know that as well. Hopefully that makes sense. M naught minus 1 is smaller than a n naught, right? So if I took one smaller than it, this would be m naught minus 1, and it would be smaller than a n. So I want the least one that satisfies this property. Okay, and now we just kind of combine all this. So we know that if I give you any two numbers a and b, any two real numbers a and b, you are able to always construct m naught and n naught that satisfies all these three inequalities. You're able to do it always. Then I can tell you that we can prove that m naught over n naught will in fact be. You just have to combine these facts now. They will in fact be. What am I trying to say? In between a and b. So now we need to show m naught over n naught is in fact between a and b. I'm not claiming this. I'm going to show this from these facts, right? And we can maybe number them. Okay. So we'll break this into two parts, right? So maybe, first part is to show that a is less than m naught over n naught. Show, indeed by 2, which tells us that m naught is less than a n naught, then obviously m naught over n naught is less than. Okay, and we're done with that. So we have the lower bound, but this is the careful construction here. We also have it that fraction it's bigger than a. That was simple. That kind of happened because of this. But actually, it's also still less than b. And that was because of our careful selection of n naught. That was why. Right? Show m naught over n naught is less than b. Right? Okay, so we have to somehow combine these two facts. I mean, that's quite literally the only way we can do this. Right? So how do we do it? I have to remember. I can tell you we're combining those two facts. So from what am I looking at? Okay, so from 3 tells us that which is m naught minus 1 is less than a n naught, which is of course equivalent to m naught is less than a n naught. Sorry, a n naught plus 1. right? And I'd love here if I could get like a, if I could get like a b n naught here, right? I'm not saying this yet, but if I could get a b n naught here, then I could just divide it over, and then that would be the end of the day, right?
Yeah, and you can get it from just from the first
From the
fact.
first one, exactly, right? That's where I was going, exactly, right? So I can get it from the first fact here, and so the first fact I can see from this. So from 1, I can get that 1 over n naught is less than b minus a, which tells us that a is smaller than b minus 1 over n naught. And combining these two facts here, right? M naught is less than a n naught plus 1, which is less than, well, I'm going to replace a with something bigger than it. So it's going to be b minus 1 over n naught times n naught plus 1, which simplifies, you just distribute it in a little bit, which simplifies into b n naught. And so then we have that m naught is less than b n naught, which means that m naught over n naught is less than b, and we are done. So overall, the point here is that I can do this careful construction saying that I am going to give you two real numbers a and b. They are distinct. One is bigger than the other. I give you that. You give me n naught and m naught that satisfy these inequalities, and I showed how here. And actually, if it satisfies these inequalities, you see combining all three inequalities, we can prove that, in fact, that fraction, m naught over n naught, is a rational number. Clearly, it's a rational number, but it's also between a and b.
Actually, so this exercise is actually it's not an exercise, right? It's a theorem in the book.
Yeah.
It's actually a great one, and it's one of the good ones to start with.
I'm with you.
I wanted to make the pause that the interruption that like again in this book they start with the real numbers without actually constructing them. But if you actually construct them and then you derive this property about the representation in a radix system, let's say the decimal system, then this theorem becomes very trivial, just from the decimal representation, because you can just say, well, A has a string representing it, B has another string, then you can take basically until which point they are equal, right, as the strings, and then you can just get to the next position. So basically the first position in which they differ, right, and then one has to be less than the other.
Yes, right.
And then you can just put something that is
now that's with like defining the reals as like the decimal expansions, right? And you construct it with as the decimal expansions, right? It's like, I guess maybe, and you can call the decimal expansions, those are the sequences, the Cauchy sequences, right? Those are the decimal expansions, right? Yeah. Exactly, right? So I'm with you. So if you constructed using Cauchy sequences, then you have these decimal expansions, then you can just do it decimal by decimal, right? Then digit by digit, I guess I mean, right? So so I'm with you for sure, right? It's just that's not how we constructed it. We didn't really construct it. We just took this kind of abstract definition. What did we use here? Let's think about what we used here. So we used R is, okay, let's remember, R is a complete ordered field with Q as a subfield, right? So what part of that did we use? Well, complete. Did we use complete? I think we did. Where did we use completeness in this? Is it obvious that I'm just missing it? Completeness, nested interval property. No, we didn't use that. Least upper bound. No, we didn't use that.
Well, we used the Archimedean property for sure.
Archimedean property we use for sure. Does the proof of the Archimedean property need the? It doesn't need the completeness.
No, it doesn't. I think you don't use the completeness here.
Yeah, I guess you're right. Right. So we used Archimedean property of R, Field, we use lots, right? Field is what lets us do all this algebra. Like, how do we know we're allowed to do this algebra, moving things around? Ordered as well. Like, how do we know we're allowed to do all these this algebra on it? Was the ordered field part of it. Yeah, you're right. I guess there's no completeness. I guess I didn't really think of that. Although I do feel like it's kind of irrelevant, but I feel like it is relevant, but I guess
It's
not.
not because
There's
you're trying to find a rational number in an interval of real
yeah,
numbers.
you're
So
right. You're right.
the
You're
bounds that you are having don't really match the completeness, right?
Yeah, I see what you mean. Right? We're not finding a real number. We're finding a rational number, right? And so we don't need completeness for that. That makes sense. Okay, I'd love to hear also from other people in the group. I don't know if you have any thoughts whatsoever. There's no stupid questions. There's no stupid thoughts. Just I'm curious what other people feel about the proof, about my presentation of the proof, if it makes sense. I don't know. I'll toss it out there. Any comments? Okay, well, I'll take that as a I did a astounding job for now. But please, if you have anything else to mention. Oh, I got a message. Something to decimal representations, real numbers, subtract. Yeah, absolutely, right? It's just that by doing that, you're saying, yeah, I see what you're saying. By doing that, you're saying that every real number has a decimal expansion, right? A decimal representation. And where does that come from, right? Like that you can prove. Of course, it's true, right? Every real number has a yeah. It doesn't have to be unique, but it at least does have a decimal expansion. And that's part of also the diagonalization argument for the uncountability of R, right? And yeah, you can kind of go with that. I mean, if you go with that definition of R, that's fine. But I prefer the proof, and it's very similar, to be honest. It's very similar because, of course, yes, every real number does have a decimal expansion, but kind of tiptoeing around that fact, you can prove uncountability using the nested interval property as well, which I forget is in this chapter. It must be in this chapter, yeah. So we can maybe talk about that in a little bit. But yeah, so this is the proof of density, and I hope it makes sense. This is, of course, as we're saying, not using decimal expansions or anything like that. Okay, well, I'm going to keep just kind of tearing through. So where are we? We still have, maybe let's make a little plan together of what we want to work on, because there's still a lot here. So I think existence of square roots, right? We can, of course, talk about this. This is a good proof. I think it's fun. And then there's some function mumbo jumbo about countable sets and uncountable sets, and we could maybe talk about some examples here. And maybe we can get into the exercises. There's things here, and then there's the last one, which is this diagonalization stuff, right? And there's not particularly a theorem in there, but we can talk about that. So I don't know, as a group, any suggestions of, do you want to see, I guess, yeah, do you want me to do this proof, the proof that root 2 is a real number?
I think it's a good one. So basically, just telling you that actually the square root of 2 exists. So I think it's
Right.
a good one to have.
I agree with you. I love it. It's honestly one of my favorite proofs. Like, if I had to name, it might not be my favorite theorem. Obviously, it's not the most astounding theorem, but I do love the proofs. Okay, so let's do it. Let's do it, and then maybe after that we can just go into exercises. Let's start doing some actual exercises from the book here. Okay, so let's go through it. Theorem, blah blah blah. And again, this is one of the ones I have done before, so I'll try to do it from memory. It's only this chapter that I'm going to be able to do things from memory. The future chapters, I'm going to need more help. This chapter, I can do. So hopefully everybody's following along. Hopefully, I don't know, nobody's falling asleep or anything. Hey, this is for everybody's enjoyment. So there's something I can do. I'm not doing this just to be a teacher or whatever. I mean, obviously I'm very happy teaching, but if there's something I can do to make it better, then just please tell me. So, and I will have the chat open as well. So if anybody wants to say anything here. Okay, so let's talk about this proof here. We know, right? Actually, I'd say proving this one from memory is harder than more complicated statements just because you can use so many tools. Yeah, it's true. There's a lot of ways to go about this. So we know that, root 2 is not in Q, right? ... So, so let's just say it ominously like that. So, well, that doesn't mean it's in R, right? I mean, I is not in Q, but I is also not in R, right? So just because it's not in Q doesn't mean it's in R, but in this case it is. Root 2 is in R. Yeah. So let's take a look here. Well, we have a few things at our disposal, right? So we have our definition of R. We have to remember what that means. So this is like what this gets into. We have our definition of R here. And so we have to prove that if there is some element that satisfies this. A good way to think about elements of R is that they are the supremum of some set, right? They are the supremum of some set. Every element of R is the supremum of a set. That's true. And every supremum is an element of R. But the supremum of every set, every element of R is the supremum of a set. That's what I'm trying to say. So we can kind of take it from that perspective. So let's do that. So I'm going to look at my notes here. So intuitively, right, this alpha, which satisfies this equation, let's define the set T. T is this set of all these numbers. So T is a real number such that T squared is less than 2. So this is the set it's not exactly the same set we talked about before. So before we talked about this being Q here. So now T is a real number. It's all the real numbers whose square is less than 2. And so the claim is that alpha is equal to the supremum of, not claim. Alpha is defined to be the supremum of T, and the claim is that alpha squared is equal to 2. Okay, that's the strategy. That's like the general strategy. Define this, claim this. I mean, if I support that claim, then we're done, right? Then I have a real number. Notably, this is in R. Okay, so let's get into the actual formal proof here, right? So proof. I don't really have to rewrite it, but T is a real number such that T squared is less than 2. Well, first of all, T is bounded above, right? Indeed, we have that, if T is in T, then this means that T squared is less than 2, which means that T squared is less than 4, which means that T is less than 2. Okay, so it's bounded above by 2. Therefore, the supremum of T is a real number, and we're good to go. And it's okay to say that alpha is that supremum because it exists. Okay, so that's kind of maybe our step 0. Step 0. I'm gonna call it step 1, I guess, but it's kind of doesn't really count. It's just kind of starting. So we're going to define alpha to be this supremum of T. Okay. And again, the claim now is that alpha squared is equal to 2. And we're going to do this by showing that alpha squared, is not less than 2. Maybe step 2 is to show this. And step 3 is to show that alpha squared is not greater than 2. Right? So if I can show that alpha squared can't be less than 2, and if it can't be bigger than 2, but it is a real number, then it must be 2. Okay. And again, just to kind of strategy here, right? So alpha squared being less than 2, this is going to imply, and the problem is that, violates that alpha is an upper bound for t, and and alpha squared being greater than 2 violates that alpha is the least upper bound. Okay, and so we'll show those contradictions. Hopefully everybody's with me so far. So the first step here, step 2, I guess I'm calling it, right? So I guess I'll open my notes again here. So suppose alpha squared is less than 2. Okay, we are going to show alpha, show what? What am I showing? Show that there exists an element of t which is greater than alpha, right? That's what we're going to do. We're going to show there exists an element of t which is greater than alpha. Okay, so alpha squared is less than 2. What we're going to do is we're going to consider an element slightly larger than alpha. So alpha plus 1 over n. Okay, and we're going to fix n, right? So consider alpha prime, which is alpha plus 1 over n. Okay, for some n in n. So this is a number just slightly bigger than alpha. Okay, well, alpha prime squared, okay, is alpha plus 1 over n squared, which is alpha squared plus 2 alpha over n plus 1 over n squared. Okay, and my goal here is to show at the end of the day that this is less than 2. Like that's the dot dot dot. If I can show that this is less than 2, that means that alpha prime is an element of t. And if alpha prime is an element of t, notably alpha prime is bigger than alpha, then alpha is not an upper bound. Okay, so this is the middle bit. We have to somehow show that that whole expression there is less than 2. So alpha prime is less than 2. So we do this. We'll give ourselves a little simplification here, just to make our lives a little bit easier, right? What we can do is we can just knock off the 2 from that, right? Because that's squaring it is going to make this smaller, which is going to make this bigger. So we can knock off the 2 from that, and then just collect everything into a common denominator. Okay, so we know alpha squared is less than 2. We just need to know if there's some way to pick n so that we can fit this so that it's still less than 2. Is there some way to pick n such that this is small enough to fit in between? Alpha squared is less than 2. So that means there's a little bit of wiggle room between alpha squared and 2. If we could make this small enough to fit in there, then it would work. So we're going to do exactly that, right? We're going to pick n equals n naught such that 2 alpha plus 1 over n is less than alpha is less than 2 minus alpha squared. Right? Again, we're allowed to do this because this is the Archimedean property in just a second, right? 1 over n less than 2 minus alpha squared over 2 alpha plus 1, right? So Archimedean property tells us that we are allowed to do this. But notably, this is really the key thing here, this equation, which is that this little bit fits in between this little gap. So continuing on here, right? So maybe I'll just kind of continue dot, 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 right? We know that this is, so alpha squared is less than 2. So you can put a 2 there. Plus, and then this 2 alpha plus 1 over n is less than 2 minus 2, no, it is 2 alpha, 2, should it be different? Did I have it? What did I do? Oh no, I'm leaving the alpha squared. Sorry, the alpha squared stays there. That expression right there, right. That expression right there is plus 2 minus alpha squared. There we go, which is equal to 2. And there we have it, right? So that is our final statement. So what's the contradiction here? Does somebody want to maybe jump in? I don't know. You have a second. There's a contradiction now. It's kind of explained on the screen, but does somebody want to take a crack at going through this and seeing what the contradiction might be?
Okay, given that nobody's saying it, I would just say
Sure.
it. So basically, that you assume that so you define alpha as the supremum, which is it's a number that is greater than any element in T, and then you just increase alpha, and you show that so this alpha prime is greater than alpha, and you show that it belongs to T. So the contradiction is that that's the contradiction basically.
Exactly, right? So the contradiction, exactly. Alpha prime is in T, and alpha prime is greater than alpha. So that can't be. So our contradiction is that we suppose this right here. So we've proven step 1, right? That's not true.
Perhaps a small remark to make here is when you're on the step 2, where you're saying suppose that alpha squared is less than 2, then you're saying, well, consider alpha prime to be just slightly bigger than alpha. One might wonder, why do you add 1 over n and not just some real epsilon, right? And well, the remark is that you are using, like, you need it to be like a rational number to apply the Archimedean property.
Yeah, good point. Exactly. Yeah, exactly, right? So I'm saying it's something, usually we say plus epsilon or something, right? But if I need to later apply the Archimedean property to be able to pin that down a little bit, to show that there is some choice. So Archimedean property gives us that property, gives us that ability, I guess, right? So, okay, good. So let's keep going here a little bit. We have the other half, and then maybe we can take a short break or something like that, or it's getting a little bit into it here, so we can maybe do some examples or something. But I think these are good examples, really. So let's do the other half, right? So step 3. If I'm numbering it correctly, I think, yeah, step 2, step 1, step 3. We're going to suppose that alpha squared is greater than 2, and we are going to get a contradiction, which is to show that we have a smaller upper bound. Okay, we have a smaller upper bound for the set. So alpha wasn't the least upper bound for the set. Okay. So we do this the other way around, right? So consider alpha prime equals alpha minus 1 over n, some smaller value, right? If we can show that alpha prime squared is greater than 2, that means that, so alpha prime squared is greater than 2. That means that alpha prime is an upper bound for T, and alpha prime is less than alpha, right? Clearly, alpha prime is less than alpha based on this. So, and that would be our contradiction. So we need to show that alpha prime squared is greater than 2.
Well, does that really mean that? Like, because I mean, I guess it makes sense just because we know the square root of, just because we know that we're dealing with positive numbers. But technically, alpha prime squared greater than 2 alone doesn't imply that alpha prime is an upper bound, right?
Well, we know that doesn't it? Because everything in for t is all the real numbers whose square is less than 2.
Right. Like my point is like the square function is not monotone.
Yeah.
Monotone, right? So here it works just because we know that alpha is greater than 1, and alpha minus 1 over n will still be kind of like perhaps greater than 0 or something. So the monotonicity still holds in that
Yeah,
case.
you're right. Are we we might be just saying here that like alpha has to be a positive real number here, just because of that this specific thing here, right?
Right.
Yeah. Okay. I mean, that might be it. I don't know. Do they say that in the text? Is that no? Or do they say right at the start? No. Oh well, no. But yeah, I guess we have to say no. But alpha would be positive. Okay, so that's not yeah. That's not a thing, right? So okay, so yes, we would separately have to show that alpha is positive or greater than 1 or something, right? And with that, then we have this factor. I think that makes sense,
Yep.
right? So that would be a separate. So there's a kind of, we can put it here like hidden claim. Alpha is greater than 1. And so that's not wild to prove, but yeah. Okay, good. Yes, good point. So now we proceed now basically the same as we did in the last one, right? So we have to prove that alpha prime squared is greater than 2. So we take alpha prime, which is alpha minus 1 over n squared, which is alpha squared minus 2 alpha over n plus 1 over n squared, right? And we want to show that this is greater than 2, right? Like ... here, greater than 2. So we want to start like chopping things off, right? So this is certainly a positive number, so we can chop that off. We can just say that we have alpha squared minus 2 alpha over n. This is true, right? Because we're adding some positive number here, so of course that's going to be bigger. And again, the inequality goes this way this time, right? So we can remove things like that. Okay, and then basically we do the same thing. So, choose, fix some n equals n naught such that, okay, what do we know? We know alpha squared is less than 2, right? So that means that, sorry, it's greater than 2. Sorry, greater than 2. So that means that alpha squared minus 2 is some number, some real number. There's some little wiggle room in there, right? So we want to fix some n such that this amount right here is less than this amount right here, so that it stays in there, such that this 2 alpha over n is less than alpha squared minus 2. You can make it negative, whatever, just to flip it or whatever, but it's pretty much the same thing. And for the same reason as before, we can do this. You can rearrange this as some Archimedean property kind of thing. So then we have that alpha squared minus, and then this would be alpha squared minus 2, right? And we get that this is just 2. And we're done there, right? Because that's a contradiction, right? That's our contradiction. Okay, so that's the whole proof. Zoom all the way out to see the whole thing. I mean, that's a little bit long, right? But so just to kind of recap here, right? We have that we're claiming that there is some real number that satisfies this. The real number is the supremum of this set. So then we can show that the supremum of the set is real, and that the supremum can't be any lower. The square of the supremum can't be any lower or bigger, and so then it must be equal to 2, right? So therefore we have that the supremum of t squared must precisely be equal to 2. That's our conclusion there. and that supremum of t is a real number, right? That's an important point. But okay, so I don't know, thoughts. Anybody have any thoughts about this one? We've been going for a little while now, right? So we're at the hour and a half mark here. I'm thinking after this we maybe try 2 examples together, and then probably call it there for today, just because it's a little bit of a shorter meeting.
You know, I think this was perhaps one of the first few things that I really liked from the book. This
Yeah.
example in particular,
Mhm.
because so like the book is trying to teach you to learn all these tools for proving, right? And in particular, the usage of very simple inequalities, right? Manipulating inequalities to obtain bounds and so on.
Yes.
So in here, you basically use some techniques that they kind of like don't make them explicit, but that they are techniques that are used everywhere. So if you
Yes.
have, if you want to prove that some expression is less than some number, you first get rid of some things, you make it you make it less than some other number, and then you prove that this other expression that is simpler, it's also less than that number, right? And the opposite for,
Mhm.
and the same thing for showing that it's greater than some other number. So
Yeah, I'm with you.
it's just very
I'm with you. Yeah.
very cool.
Yeah, I get what you're saying. So like, it introduces a lot of these kind of principles and techniques that we have in proving things in analysis without explicitly saying this is a common technique. It's just like, let's just do it. Just comes up here, right? You shuffle things around and you shuffle inequalities around, and you get what you want.
Yeah, and in particular in this example, they kind of like tell you, like, they tell you what is the idea of the proof, and then they proceed with the proof. So in a way, the student that it's fresh with analysis or with formal mathematics,
Yeah.
get a sense of what's happening before actually seeing it, so
Mhm.
you don't get lost through the proof, right?
Right. I think it's well put together. I agree with you. Good. Okay. So why don't we take just 5 minutes or something like that? Let's take a little 5-minute break, and then why don't we choose some examples? I got 2 suggestions for examples, so maybe we can take a look at it, right? So the examples of 1.2.6. 1.2.6 was the suggestion. Where am I? 2.6. Okay. De Morgan's just D. Oh, 1.2.6. Sorry, not De Morgan's. This one. D. Prove this. Yeah, so it's like the reverse, the other side of the triangle inequality. So that's good. Yeah, we can do that. And then 1.5 point. So maybe I'll take a picture actually. 0.2.6 D, and then 1.5.9 was the other suggestion. We'll start with this. If anybody has any other suggestions, then we can do it. Oh yeah, 1.5.9 is good. I don't know. I don't think I've done this one fully, so maybe we can talk about this a little bit. And honestly, I think that probably will be enough for today. So hopefully that's okay with everybody. We do these 2 examples. But let's take 5 minutes. Cool with everybody? So it's 34 on the hour, 8:34 for me right now. So at 8:40 we can come back. So hopefully everybody's back. We're back in a second, we'll get back to it. Good to take a break every once in a while. So yeah, let's do these 2 examples and probably call it a day there. Maybe we missed a couple things from the end. We could maybe continue talking a little bit about chapter 2 another time as well. Chapter 1, but anyways, I think that's probably good. Those are the main things. So let's take a look at this. So just part D is the important thing here, right? So we have that we want to prove this. Okay, so for part D, we want to prove that the absolute value, I should zoom in a little bit. The absolute value of A minus the absolute value of B is less than the absolute value of A minus B. And it's telling us that A is A minus B plus B. Right. So we have the regular triangle inequality. So the regular triangle inequality is this. So that's what we need to show, right? So we know that the regular inequality is that A minus B is less than or equal to the absolute value of A plus the absolute value of B. No, what am I saying? Absolute value of a plus b is less the absolute. That's what I'm trying to say. So we have this. Okay. We somehow need to conclude this up here. Well, the first thing is that I need to have a minus b, the absolute value of a minus b. So we can rewrite a, right? We could say this is the absolute value of, how should we do this? A minus b plus b plus b. Does that work? Because then this is right. So this is the same thing as a minus b, or a plus b. I mean a plus b. So this should be. But what would that do for us, right? So we would get that this is the absolute value of a minus b plus b, right?
Yeah, but
and-
like, don't you want to show something with the differences rather than with the addition? I guess that what you have to apply
Yeah.
this subtraction and addition should be not on a plus b, but on well, something with the subtraction somewhere rather than
So,
doing the-
something
I
with
guess
what? Sorry, with what?
something with a subtraction of a and b.
Oh, a
rather than
subtraction of a
having
and b.
them.
Well, that's why I did this because we got an a minus b here, right? That was
Yeah,
kind
but
of
like you will always get it, right? Just
Yeah.
because you will always subtract b and add b back.
yeah, right.
So
So here we have a plus b is less than or equal to the absolute value of a minus b plus 2 absolute value of b, right? And that doesn't look right. That doesn't tell us anything, right? Because we have that.
I think we could use like a absolute value of a minus b plus b, because that's equal to absolute value of a, and then
Mhm.
use triangle inequality, and instead of absolute value of b, we will just have absolute value of b, and then subtract it to the other absolute value of a.
Okay, so let me go through that. So we have that a is equal to a minus whatever it doesn't matter the order, right? But a minus b plus b, and we take the absolute value of both sides here. So this is the absolute value of a minus b plus b,
Exactly, yeah.
which is less than or equal to the absolute value of a minus b plus the absolute value of b. Well, there you go. And then you have that the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. And we can just take the absolute value of both sides. That's a positive number.
No, I think we need to do like the same thing, but like
the other
like,
way. Yeah. Right,
exactly,
right. Right. So then we can. So that's maybe part one, and then part two is that we have that b is b minus a plus a, and so then we have the absolute value of b is the absolute b. B minus a plus a, which is less than or equal to the absolute value of b minus a plus the absolute value of a. And so we have that the absolute value of b minus the absolute value of a is less than the absolute value of b minus a. And so we can, do however you want to do this, right? So we can pull you can flip this because it's absolute value, right? So this is equal to the absolute value of a minus b. And so we have that here, right? And then this is just the negative absolute value of a minus the absolute value of b is less than or equal to absolute value of a minus b, right? So we have that. Does that tell us? Is that what we want to have? This is the same as.
Yeah, this is the solution that the solution that I ended up doing. I wanted to show that absolute value of a minus absolute value of b is less than that or equal to that. And then I showed that the absolute value of b minus the absolute value of a is less than or equal to that. So that should imply that the absolute value of the absolute value of a minus the absolute value of b is less than or equal to that.
Is less than or equal to, yeah, right. Like we're combining this into the final statement. That like 1 and 2 gives that the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. I'm just not quite sure that combines like that. Why does that combine like that? Why am I just being silly? Why does that combine like that?
Because I think the absolute value of the absolute
We
value
can
of a,
flip the
Yeah, hold on. Finish what you're saying? Yeah.
sorry. We can flip the negative sign on inequality 2, and then basically minus
This is
yeah.
the absolute value of a minus the absolute value of b is greater than the absolute value of a minus b, like this. And so
with a negative,
yes, then that combines. Well, hold on. Is it? No.
I think it's missing a negative sign on absolute value.
Yes. Like that, right?
Yeah.
Yes. Then this does imply that. Yes. Good. Then we're done. Perfect. Okay. Are we good? Is everybody good? Including the person who asked the question originally?
yeah.
Yeah. Any hopefully nobody has any heartaches with this. Hopefully it's okay. So yeah, that makes sense, right? We combine it in each direction, and then just the part that, this is this, and then of course if you have this quantity here that is bounded above by this and below by negative the same thing, then the absolute value of that is less than the thing. Good. Okay, that's that question. Now let's take a look at this next one here. 1.5.9. So 1.5.9. Real number x is called algebraic if there exists integers, not all 0, such that polynomial with those coefficients, x is a root of that polynomial with those coefficients. So a real number is algebraic if it is the root of a polynomial with integer coefficients. Sorry. Real numbers that are not algebraic are called transcendental. Reread the last paragraph of section 1.1. The final question posed here is closely related to that question of whether or not transcendental numbers exist. Well, let's just, out of curiosity, let's just see what's at the end of 1.1 just to I guess motivate this. Right? Is there a kind of symmetry? Not surprisingly, other roots such as are often irrational. Can all irrational numbers be expressed as algebraic combinations of nth roots and rational numbers, or are there still other irrational numbers beyond this? That's an important one. Right? That's the thing. So we know that all the roots and stuff like that are irrational, except the obvious ones from 1.1. But this is going to be kind of showing that it's not just those. So show that root 2 and blah 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 are algebraic. Okay, well let's just start with that, right? So this is just some kind of fun algebra. So of course x squared minus 2 equals 0. Root 2 is a root of this, right? So for root 2, that's our polynomial. For the cube root of 2, we can do x cubed minus 2 equals 0. Right? Okay. Then, so hopefully that's pretty clear, right? So that means it is algebraic because there is a polynomial that has it as a root, and the polynomial has integer coefficients. Okay, the last one for root 3 plus root 2, right? We need this to be the root of a polynomial.
Yeah, so I guess that you could say x equal to this, and then start kind of like going backwards, squaring, for instance. And then I guess at some point you have to move around things around a little bit, but that should probably work, right? So if you
I'm with
square
you.
the
I
first
think
time,
that makes sense, right? X squared is going to be equal to, so what's going to be 3 plus root 6 plus 2,
mhm.
and then so that's 5 plus root 6, and then we can probably square it again, x to the
Well,
4.
but it's better to if you square now, you get a problem because you will still have some squared root, and then that's a problem because you want the coefficients
Yeah.
of the polynomial to be rational. So perhaps you can
Mhm.
pass everything to one side, so that when you square the square root, you get rid of the square root.
So
So
like x
basically, you
squared minus
subtract
5 equals root 6,
Mhm.
like this, you're saying?
Right, like that. Yeah, something like that.
Yeah. So it's x squared minus 5 squared equals 6. And and then now you can say this is like x to the 4 minus 10x to the 2 minus or plus
No, plus
plus
21.
20, whatever. Well, 25 equals 6, whatever. And then you have your
Okay.
coefficients here, right? X to the 4 minus 10x squared plus 19 equals 0. And there we go. And there's our polynomial. So we know that x has to, x being this number satisfies this because that's kind of what we started with. It's kind of the equivalent thing. And then we just have to get it to a point where it's all integers. So we see that it is algebraic. So, okay, that's A. Let's read B carefully. So let's just do it. So fix n, natural number. Let an be the algebraic numbers obtained as roots of polynomials with integer coefficients that have degree exactly n. Using the fact that every polynomial has a finite number of roots, show that an is countable. Okay,
Right.
so let's
Actually, that one took me a while to get it.
Mhm.
At least the way I did it. If you want,
Mhm.
I can explain how I did it.
Yeah, in a second. Maybe I'll just like describe it a little bit first, and then yeah, sounds good. Right. So let's just understand what the sets are that we're working with here, right? An algebraic numbers obtained as roots of polynomials, so they are roots of I'll just write it, I guess, polynomials of degree exactly n. So this means that if x is in an, this means that there exists some a whatever, however they used it, an, some an x to the n plus ... plus a0. There exists a i's such that that is true. For that same n, right? For that same n, like that. We have to show that an is countable, for some fixed n. So of course we could try to. There's a lot of methods here. So I'd have to think. So maybe now we can maybe open it to discussion. I don't know if someone has an idea here, just slowly.
Yeah. So let's see. Like, I remember that when I tried to solve it, it was a while ago, but there was something like I first need to show that the polynomials with integer coefficients are actually countable. And I kind of proved it. So I know that it can be proven by just mapping the polynomials of degree n of integer coefficients with the Cartesian product of the natural numbers of length n plus 1. But for not using that, like in order to use simpler math, I proved it by induction. So I started with degree, I guess 2, or degree 1, and then I just kind of like proved by induction that if you add a new coefficient, you can still count those polynomials.
Yeah. Let's try both. I don't know. Let's try both. So method 1. I like what you're saying though about so the set of all polynomials with integer coefficients of degree n, I forget how they notate it, but something like this, right? We'll see it in linear algebra, is isomorphic to Zn.
I guess
right?
n plus 1
because
you have. Like
say it again,
if
sorry.
the degree is n, then you have n plus 1.
Oh yeah. Right. And this is, we could just kind of skip some steps here, but there's however many steps you want to skip, but this is certainly countable. Right. So that since the number of polynomials of degree n with integer coefficients is countable, times a finite number of roots, per polynomial, then that means that an is countable. Of course, we can show these bijections and things like this, right? But that means that this is countable. So I think I don't know if there's any comments on this. Obviously, we could make this more rigorous, but I'm interested in the induction as well. So maybe we can think about the induction. But I don't know. Is there any comments on this? I think that's a complete proof for that.
Oh, I have something to say.
Yes.
I admittedly had to ask Zero Aleph Zeta for help with this one.
Right,
and
yeah.
He mentioned something called the height of the polynomial, which is useful for this.
And what is that?
I think it's like the absolute value of a sub 0 plus the absolute value of a sub 1 plus ...
Okay,
plus the
okay.
absolute value of a sub n.
Mhm.
So we start by examining all polynomials with height, I guess, 1,
Okay.
and
Yeah.
finding the
Yeah.
roots, ordering them, then height 2, and so on and so forth.
Sure. I think that might be a similar, like, that sounds a little induction-y, but or I'm sure it's also somehow related to this. I probably have to see more about that. I don't know very much about polynomial height. I don't know. Like, this is my first time hearing that term. Yeah. So why don't we proceed by induction here on with this other strategy? But we can of course talk about that after too. I like it.
So the induction, I guess, would be to prove the countability of Pn, and then the rest of the argument stands.
Right. Well, for the count, yes, because the rest of it is the same here, right? So, the countability of Pn, but Pn is clearly isomorphic to this, right? So we just need the countability of that,
I guess, yeah.
right? So actually, it's not really method 2, because in this I kind of just said it, but we can just show that, z n plus 1, like this is what we need to show. I mean, that's really it. That's the count. Like that's the same thing. So let's do it. How do we do it? I don't know. I mean, think for a second here, right? So what is Zn? Zn plus 1 is a tuple of, how should we, n1, n2. Well, no, I can't call it n. m1, m2, ... mn plus 1, right? So is an element of z n plus 1 and they're all integers. Right? And we have to show that there is some kind of mapping between this and the natural numbers.
Right. So the induction, I guess, uses this important theorem that the countable union of countable sets is also countable.
Mm-hmm.
Because in that case, what happens? If you assume that Zn is countable, then when you add a new component to the vector, so to have n plus 1 elements, then for each possible integer number in that last component, you have a set of vectors from Zn. That
And they're all countable.
A new integer, right? They are all countable, and then you have a countable set of them. So then the union is countable, and then that's the inductive step.
Yeah. Okay, let's do it. Let's write it out.
Yeah. Okay.
Right. So for n equal to 1, we have that, or even 0, I guess. N equal to 0. We have that z 1 is isomorphic to n. I don't think we have to show this, right? This is fine. This is that thing, right? That's the flipping back and forth. Did I just make sure I did click record again? Yes, I did. Good. So that's easy. So now, for suppose Z to the K is isomorphic to N. Show Z to the K plus 1 is also isomorphic to N, right? Well, the point is that you're saying that Z K plus 1 is equal to the set of how should we write this? It's like an element. Well, I guess it's K elements, right? Followed by one more K and then one more like that, and they're all in Z, these elements. I mean, everything's in Z here. And this is equal to the countable union. How should I write this? I just don't know how to write this. So this is like I have this amount here, followed
I guess
by
that you can define it like, okay, let A sub n or A sub whatever, A sub I be A sub I sub k or whatever, the set of all sequences of size k plus 1, where the first or the last item is exactly equal to I, right? And then you're taking the union over those.
Right. So it's the union, the countable union of all these. I'll call it B or something, just because we have A from before. B, I or something. Yeah. Right. Where BI is equal to these kind of tuples of length K plus 1, where the last element is I. Like that. And the union goes, how should I, from negative infinity to infinity, right? That's kind of a bad notation, but it's I is in Z. I should just say, I guess that's all I can say, right? And each of those are countable, so that's important, right? BI is countable, since we assumed that Z to the K is countable. And because it's just Z to the K accountable plus one more, countable amount plus one more, and it's the union of all these countable things. So then we have the result, right? Therefore, Z to the K plus 1 is countable. So yeah, I'm okay. I'm okay with that. I don't know if everybody else is okay with that, but that seems to make sense to me. Right, where we represent Z to the K plus 1 as this countable union of these countable sets. So of course Z to the K plus 1 is countable itself, and these sets are countable because by induction, right? Because they're made in part of a smaller set extending it, right? And those smaller sets are countable, and we're extending it by just adding one more element.
Yeah. So perhaps a remark here is that you're claiming isomorphisms, but technically, what you need, okay, maybe I'm wrong, but like an isomorphism, it has some kind of algebraic properties, right? And here you just need the bijection, or maybe.
Well, I think in the case of just these sets, I think that that's the same thing. That the bijection, right, in the specific case. Yes, isomorphisms between different other kinds of objects for sure need some algebraic properties, right? But here there's no algebraic properties. That's my take. I don't know. That's my. Okay, and let's finish up. So we know that the algebraic numbers are all, the HAN is countable. Right? Now argue that the set of all algebraic numbers is countable. Well, that's pretty much the same thing, right? Because we can just say, fancy A is the set of all algebraic numbers. Well, it is the union of all the ANs, right? And N is going, let's just say N is a natural number. And so therefore, it's the union of a bunch of countable, it's the countable union of a bunch of countable sets. So this means it's countable. Okay, and so what can you conclude about the transcendental numbers, right? So we know that R is equal to the irrational numbers union with the rational numbers. I is uncountable, right? I is the algebraic numbers union with the transcendental numbers. I don't have a symbol, so I'll just say that, right? If these are all countable,
Well,
yeah,
never mind.
then these must be uncountable because this is uncountable. And so the transcendental numbers must be uncountable. The ones that are not algebraic. And there you have it. Okay, guys. Well, that's that. We've been going for about 2 hours now, so I think that's probably a good place to wrap it up just for today. I meant for today to be a little shorter, but we ended up not even finishing really everything. I mean, we did, but so there's a couple more things. Cardinality. We've been talking about cardinality, right? That was just from one point. This is what we've been talking about in this example. So I think that was a good example to do. And then there was all from 1.6, everything from 1.6, which is just a bunch of more like set theory stuff, which is interesting and I think is a good exercise to do. And some things that are kind of challenging. Particularly, I would love to go through this guy. I've never been able to fully do this one. Even reading online, I don't think I've been able to fully understand this one yet. So, yeah.
I can comment on this one. I was actually teaching a class in discrete mathematics some time ago to some computer science students, and for me it was kind of hard to completely show the proof. Actually, I didn't understand it by that time, so I just kind of like gave some graphical intuition of how it goes. And then after I read this specific exercise and I tried to follow along the examples, I was able to understand it and to follow along. So it's definitely a must do this specific exercise.
Yeah. I agree. One time I was sitting in front of a chalkboard and I tried this one, and I think I made progress. I think I do vaguely get what's happening, but I don't have I can't write it out fully in a way that I'm I understand everything that's going on. So maybe it's probably good not today, but maybe next time we can talk about this at the beginning and then move on to chapter 2. I think this is I agree with you. This is an important one that we should probably talk about.
Yeah, it's actually important because they for example in the theorem 1.5.6, which is just stating that the rationals are countable, right? They try to show that there is a bijection with the natural numbers, well, whatever, with the integers perhaps. And they kind of don't show it. Instead, what they show is that there are two injections, one from the rationals to the integers and one from the integers to the rationals. And they don't say explicitly that this theorem of Schroeder-Bernstein guarantees the existence of the bijection. They just say that the bijection can be built from those two injections, but it's just too complicated to write.
Yeah. For sure. I agree with you. It's very important. I've used it before. I've used it as in exactly what you're saying, right? You can use it and it's very useful. But actually going through the proof is challenging. So maybe I think that would be worth it. That's the only thing left in this chapter that I really do want to talk about. So maybe we can start next time talking about this and then move on to chapter 2 stuff. I don't know. Hopefully that sounds good with everybody. And I'll prepare it. I'll try to prepare for next time. I'll try to get this in a state that I can actually present it. Because right now, I mean, we could go through it, but it would take probably a while. So, anyways, so I'll stop recording.